I'm now starting chapter 3 of my course called linear algebra, and I'm finally getting to linear algebra. Um, Here's a system of simultaneous linear algebraic equations. In this case, it's 3 equations and 3 unknowns. And now that we know how to do matrix arithmetic, convince yourself that this matrix formulation is equivalent to these 3 scalar equations. Here I have 2x1 plus 6x2 plus x3 equals 7. That's that first equation, etc. And the format is ax equals b. This is the central equation to this whole course. And we're going to explore that a little bit. First, we'll look at a couple of geometric interpretations or views. In this case, take a 2 by 2 case, for example. The row picture says, look at the rows. The top row is just the equation itself, 2x minus y equals 0. One equation and 2 unknowns is a line in the xy plane. I can formulate it as y as a function of x. Same thing with the other row. It's another equation. It's an equation of a line. This top row, its equation is this blue line. The bottom row, its equation is this orange or yellow line. And where they meet is the solution. You probably saw this in high school when you first learned about simultaneous equations. Other possibilities, you could have the 2 lines intersect, like in that example, at a single point, and that is your solution. A single unique solution. If the 2 lines really are the same line, these equations, you have an infinite number of solutions. Any point along that line is a solution. Third case, you have 2 parallel lines that don't intersect anywhere, you have no solution. We're going to see this come up more often. Exactly one solution, an infinite number, or no solution. Now the column picture. Remember, we could look at matrix multiplication like this, a matrix times a vector, as a linear combination of the column vectors of A. And here the weighting would be x and the y. So here's a vector, 2 minus 1, which comes from this first column. That's this blue thing here on the left. And minus 1, 2 is this yellow thing here on the left. We want to know what weightings, what x and y. If I multiply this vector by something and this vector by something and add them up, gives me this vector, this red vector here. That x and y is your solution. So this is the column picture. Definition of the column space is everything you could hit on the right side with these column vectors. That there'd be some linear combination of these column vectors that would give you your column space. In this case, these 2 vectors, since they're not linear or scalar multiples of each other, are linearly independent. So these 2 guys, these 2 column vectors span the whole 2-dimensional space. I could find some x and y that would give me any point in the xy plane that you want to hit. So the column space here is all of 2D, xy plane. If you look at this other different example, this column is a scalar multiple of this column, so they are not linearly independent. All you would get is the only b's you could hit are multiples of this vector 2 minus 1. Multiples of this vector are multiples of this vector. It's the same thing. So all you get in this case for a column space is that line, not all of 2D. But anyway, that's what the column space means. What possible things could you have on the right side of your equation? Quickly, a couple more pictures. If you went up to 3 dimensions, not just X and Y, but X, Y, Z, that row picture, instead of a line, becomes a plane. And you're looking for the intersection of planes. If they all intersect at a point, that's your one unique solution. If all 3 intersect at, say, a line or a plane, you get an infinite number of solutions. And if they never all intersect at the same place, maybe 2 at a time could intersect, but they don't all 3 intersect at the same point or line or plane, then you have no solution. So that's the row picture for 3D, or it's beyond 3D. We can't draw it, can't have trouble imagining it. What about the column picture for 3D? Whoops, let's say I'm in 3D space, X, Y, and Z, but I'm given only 2 columns. So I have these 2 vectors. Well, they will span a plane. Two vectors like that define a plane. So my column space would be that plane. Any linear combination of these 2 column vectors would be a vector somewhere in that plane. So that plane would be your column space in that case. If you were given a 3rd column that does not lie on that plane, is somewhere out of that plane, then a linear combination could hit anything in the whole XYZ space. Then the column space is all of R3, 3D space. And even if it were more than XYZ, say N, but you're only given 2, call that a hyperplane, I guess. That would be your column. So that's a couple of views, row views, column views. We'll get into solving AX later. Next.